only. However, some configurations like shell and tube heat exchanger or like simple cross-flow arrangements and compact heat exchangers can actually lead to some complications. So there's a relatively simple way to address this. Okay, this has it. Okay, so tube and cross-flow arrangements. We define log mean temperature difference with a correction factor. And the log mean temperature difference based on, we correct this according to the log mean temperature difference based on the counterflow. So this one, let me write this, corresponds to counterflow. And this one is the correction factor that we are using. And where is this correction factor is coming from? So correction factor is a function of temperature differences, but they're not exactly defined in the way that we are very used to. So let me clearly identify them. That's a function of two parameters, P and R, where, for instance, what I mean P is the temperature difference, small temperature difference, TI/TO, divided by the inlet temperature of one fluid minus the outlet temperature of the other fluid. At this point, maybe I should go ahead and show you this. What do I mean by these different temperatures? T is not time. Small t is not time. It's a temperature. For instance, for a shell and tube heat exchanger, small t corresponds always to the tube side. So the temperature associated with the tube side is small t. Temperature associated with the shell side is capital T. And this is tube side. Okay. And then now I think it's clear what I'm trying to define. The temperature ratio P is given by tube side temperature difference, inlet and outlet temperature difference, divided by shell side temperature, inlet temperature minus the tube side inlet temperature. So let's define the other parameter R. R is equal to the inlet and outlet temperatures difference of the shell side and inlet and outlet temperature difference of the tube side. If you consider this, try to consider various cases how these ratios work out, you are going to see that both of them are between 0 and 1. And important observation is that it doesn't matter whether tube side is hot or shell side is hot, right? Doesn't matter. It doesn't matter. Simply, that's the designation we are using. We can extend this designation to other flow arrangements, for instance, cross-flow arrangements. And notice that when we were discussing shell and tube heat exchanger, tube side is unmixed and shell side is the mixed flow, right? Shell flow can actually, can mix across different cross sections of the heat exchanger, but tube side fluid is distributed across individual tubes, no mixing. So we can extend this understanding and always label the unmixed side with the small t. For instance, when there's tube flow, let me use this again red. Okay. So tube side, that's unmixed. And then this external flow side is mixed and indicated with the capital T. But then what happens when you have both fluids unmixed? Then you are going to essentially can identify either one of them as unmixed. For instance, here you can pick one, T unmixed, and the other one, T, also becomes unmixed, or other way around. Okay, my notes are all over the place here. And follow the designations in the following figures. I'm going to show you to actually decide on which side is the unmixed part, which side is, or which side should be labeled as small t, which side should be labeled as capital T, right? Okay, I don't want to make this any more confusing for you. Let me show you some figures. It will become clear. Okay, so here is one. Okay, so one for an one shell, two tube pass heat exchanger, and you can see the designation here. You can, based on this knowledge, based on inlet and outlet temperatures, you can calculate both P and R. And as we noticed, this correction factor F is a function of both, and you can decide on that. How about, let me show you another one. This is for multi-pass heat exchanger. And again, you can calculate R and P and use these. So all of those figures, for instance, here, there is, remember that these lanes are saying that this fluid is unmixed. So it's labeled by small t, as I mentioned. But then this is mixed, it is labeled as capital T. Here, it doesn't matter. So you can try this figure by flipping the order of t and small t, and then you should be able to obtain the same result because the situation is symmetric here with respect to the case. You don't understand from the figures, you can do the calculation. I mean, there is not really much of an interpretation in that sense, but for instance, if you flip the orders of those, one of them becomes the reciprocal of the other, minus the reciprocal of the other, and they correspond to the same F value if you do the calculation. Okay, so I would like to emphasize a few things. The limiting behavior, for instance. For instance, when I look at P going to 0, all of these curves for different R's are converging. What does this mean? That means the unmixed side or tube side is actually this delta T. Now, that is P going to 0, that side, right? And the second one is R is decreasing in that direction. If you extend this line, you are going to see that when R is equal to 0, we are actually approaching kind of this curve. Both of them, in that case, F is approaching unity. And this one indicates that delta T, small t is going to 0. This one indicates that capital T is going to 0. If you look at the calculation, that's the only way that can happen. And these are corresponding to individually phase change behavior, right? So in other words, we are obtaining this insight that regardless of the heat exchanger type, whether it's a shell and tube heat exchanger, again, you're also seeing this limiting behavior abide with an, much sharper drop. But if you go and say, the R is 0, you are going to obtain again this. So for either P or R going to 0, we are going to obtain F is equal to 1 for both cases. And this is signifying the fact that when there is phase change, it doesn't matter the type of the heat exchanger. For an evaporator or condenser, um, for an evaporator or condenser, F is going to be equal to 1, and you are going to treat the heat exchanger as a counterflow heat exchanger. Let me write this down. And a good example to this is when there is phase change. That means your heat exchanger is either an evaporator It is helpful to remember the special case with the evaporators and condensers, because remember that in the case of log mean temperature difference, we also discussed that special case because we based our analysis on sensible heat effects. So consideration of latent heat effects is actually falls outside the log mean temperature difference analysis. So that's actually saying T going to infinity, we are actually approximating phase change behavior, but that's not exactly true, right? That's as if saying that viscosity of a solid is infinity. But viscosity is a fluid property. It's not defined for a solid, but fluids approximate solid behavior as viscosity goes to infinity. But that's kind of the same idea. I mean, this is a sensible heat parameter, heat capacity, right? But as it goes to infinity, we are approximating the phase change behavior. Okay, so this is treated as, remember, the correction factor was actually correcting counterflow log mean temperature difference. So regardless of whether it's a shell and tube heat exchanger evaporator based on a compact heat exchanger, shell and tube heat exchanger, it doesn't matter. You're going to treat it as a counterflow heat exchanger with F is equal to 1 delta T log mean calculated based on counterflow arrangement. Any questions? Oh, I think there are some. Let me check. Oh, okay. Burhan is asking. I was going to mention that. Okay, if you look at ODTÜ class, there is supplemental information. So there's a PDF on your ODTÜ class website. And starting from here, that's actually one of the sections in that supplemental material. These materials were included in the previous versions of the textbook. For some reason, Incropera and David and the authors decided that they would like to exclude it in recent versions, but we find it to be important. That's why we are discussing in class. And you have access to this supplemental material PDF on ODTÜ class website. Print this out, bring it to the exam. Okay, just like your textbook. Yes, that's right. So these figures are from, I'm not showing you anything other than what's available in your textbook or the supplemental material. It's not a very long PDF. It's covering two topics. One of those topics is this, and the second one is compact heat exchangers that we are going to be discussing briefly again. Okay, so I would like to give you one remark about log mean temperature difference method. I have been, recalling this our chapter 8 discussion, and if you remember, we also discussed this when we were talking about tube banks, right? Flow across a tube bank. Do you see a common pattern emerging out of these? So log mean temperature difference turns out to be an appropriate way of analyzing the problem when heat transfer is appropriate. When heat transfer occurs in a proportional way to an temperature difference between two objects that are exponentially changing with respect to either location or time. Let me actually write this without butchering it. difference between two objects. Across location or time. I would like to emphasize this aspect. We have been discussing this with respect to location in chapter 8 and here, but you can actually do this with respect to time. So check out 11.8, example 11.8 in your textbook for reinterpretation of Lambda capacitance method. The problem associated with Lambda capacitance method, you can solve it with Lambda capacitance method. It turns out that the formulation is actually leading to a log mean temperature difference method. Okay, the idea is, I like these little Easter eggs. Well, not exactly Easter eggs, but I really like this discussion because it's a little bit personal. I will tell you why. Okay, so remember this figure when we were talking about log mean temperature difference? It is the length of the heat exchanger, but what if it was time? Imagine that you have two objects brought in contact, call them A and B. And there is a thermal resistance between them. And over time, when you bring them together, that's the typical example for the, what's that called? Zeroth law of thermodynamics, right? Definition of temperature. We bring two objects with different temperatures, and when they reach equilibrium, that means they have the same temperature equivalence. But we were interested in the transient problem. Then you would actually, you will guess that I was horrified to realize that I actually asked a midterm question to you guys last semester that had an answer in the, in one of the example problems. So if you look at example 11.8, that's actually solution of the midterm question. Okay, I wasn't aware of that, and you weren't aware of that. But it turns out, yeah, I didn't notice this example problem was actually touching on the Lambda capacitance method. And we formulated the problem by writing two Lambda capacitance equations for two slabs A and B, subtracting them so that we got the temperature difference. But then the problem reduces to Lambda capacitance. I'm sorry, log mean temperature difference. So you can actually look at the example problem. It's the exact same solution as was expected in the midterm question. Yes, but I don't think I'm going to ask that question again. So yeah, there you go now. That's spoiled already. Okay, all right. So that's why I kind of find it personal, this part. But why I didn't realize that there was an example problem in the textbook. I thought the question was original. All right. Yes, that's actually ChatGPT is yet another challenge that we are having nowadays. Okay, let's solve not a personal example problem. This is not personal. Okay, so this is 11.28, 23. And it is talking about the concentric heat exchanger. There's a figure associated with that, and your textbook, it courtesy provided us with the properties, properties associated with the fluids. As a concentric tube heat exchanger, there's cooling lubrication oil. There's a thin-walled tube carrying water inside, and the outer annulus is carrying oil. And the convection heat transfer coefficient, the overall heat transfer coefficient is given. We know the heat exchanger is operating in counterflow arrangement. And we know the outlet temperature of the oil, determine the total heat transfer and outlet temperature of water. And secondly, determine the length required for the heat exchanger. So let's do that. So I'm going to go ahead and lay out how you solve a typical heat exchanger problem. You would first start by writing out the fluid properties and whatever is being known with the associated with the fluid. Hot fluid mass flow rate is equal to that's mass flow rate of oil. That's going to be 0.1 kilogram per second. The specific heat of the hot fluid is going to be specific heat of the oil given in the table. That's 1900 joule per kilogram Kelvin. Together, it always makes sense to actually calculate the heat capacity rate. That's m dot h CPH. That's going to give us 190 watt per Kelvin. What else? The temperature of the hot fluid at the inlet is going to be 100 degrees Celsius. And the outlet temperature of the hot fluid is also given. It says oil is exiting at 60 degrees Celsius. Great. How about the cold fluid? Let's take a look. Okay, so that's water, mass flow rate, same. And the specific heat of the cold fluid is given as well. Together, the heat capacity rate of the cold fluid is, you can calculate it. I already show you how to do it, so you can do it. And 30 degrees. The question is, what is the outlet temperature of the cold fluid, water? And that's in part A. What is the heat transfer rate? These are in part A. And second, it's being asked us, what is the length of the heat exchanger? Now, you should understand that the length is, here is literally the length because that's a double pipe, heat exchanger. It has a certain length. But when we talk about other heat exchanger types, when we say length of the heat exchanger, you should understand, or size of the heat exchanger, you should understand the heat transfer area. Okay, so what is length of the heat exchanger? That's in part B. So in part A, we are going to use the overall energy balance. Well, the heat transfer rate, let me write this, equal to the hot fluid inlet temperature minus the hot fluid outlet temperature. That's equal to the heat capacity rate of the cold fluid outlet temperature minus the cold fluid inlet temperature. What are we assuming here with this equality? Any heat from the hot fluid is actually being transferred to the cold fluid. There are no losses to the surroundings. That's generally what is designed in a heat exchanger. That's why probably the outer surface is insulated. Okay. So the good thing is, when you have at least two of those temperatures known, and the mass flow rates and the properties of the fluids are known, it's simple to calculate this one, right? It's simple to calculate the remaining fluid property. And we are going to need the heat transfer rate as well. We are going to calculate it from the hot fluid side. That's going to give us 7.6 kilowatts. That's one answer to our problem. So how about the cold fluid temperature? We can formulate it. So in essence, what we are doing is MC delta T, right? This is, you have already been doing this for several years, including high school. Okay. But now, how are we going to relate this heat transfer rate to the size of the heat exchanger or length of the heat exchanger? We need the overall heat transfer coefficient, which is fortunately for us given in the problem statement. UA delta T log mean, and U is given as 60 watt per meter square Kelvin. The area, we need to formulate it in terms of the length. The log mean temperature difference is going to be based on counterflow arrangement, right? Because the problem is given as a counterflow heat exchanger. I'm going to go ahead. You can pick any site, but I'm going to go ahead and pick the inlet of the hot fluid as my site 1. That's corresponding to the outlet of the cold fluid. And that's going to be 100 minus 48.1. And that's going to be 51.9 degrees Celsius. And delta T2 is going to be the cold fluid inlet, hot fluid outlet temperature minus the cold fluid inlet temperature. And that's going to be 60 minus 30, that's 30 degrees Celsius. Remember that this is due to counterflow heat exchanger. From here, log mean temperature difference 9 minus 30 divided by natural logarithm of 51.9 divided by 30, and this temperature difference is somewhere between these two limiting values. That's always the case, 40 degrees Celsius. And the length of the heat exchanger is going to be Q divided by U pi di delta T log mean, and that's going to give us 7.6 times 10 to the power 3 divided by 60 times pi times 0.025 times 40. From here, you obtain length as 40.3 meters. That's the result. I'm going to talk about this briefly, but you probably realize that the problem that we have been solving is essentially we are given the flow conditions. We even know the outlet conditions, but we are being asked to actually determine the size of the heat exchanger. This is what's called a heat exchanger sizing or design problem. So you're actually designing a heat exchanger from scratch rather than picking one from the shelf. Okay, so how about this time some calculations. So now we have a counterflow heat exchanger, and there is hot water coming in at 90 degrees Celsius. We know the mass flow rate and specific heat, meaning we know heat capacity rate. And air is entering at 20 degrees, so it's cold fluid. We also know the heat capacity rate for air. I'm asking you, what is the maximum heat transfer rate in kilowatts that is achievable in this configuration? I actually was going to bring you something to write on, but it doesn't matter. Let's actually do a user response. And I'm going to ask you what's the number you get as well. Okay? It's a simple calculation. Oh, let me copy and paste question. Are you guys done? Okay, you're thinking about it. Okay, all right. I don't. Yeah, I think that's fine. You can talk to each other. I'm still waiting for remote responses. I don't want to influence their response by having them hear you. But I feel like Burhan is the only person listening to the lecture. He's the person asking questions, and then unfortunately John is not here. Yes, exactly right. John is also another person, but I think exam crippled us today. I was expecting this to be much more fun. Okay, so okay, so all right, there is one answer from the remote session. I think other people are reserving their energy for the exam they're going to have. And how about you? What did you got? 140 kilowatts on one answer. Burhan got the same result. How about you? We are still working on. Okay. All right, that's fine. And the answer is correct. Yes. And here is then another scenario for you guys. I just reversed. Water is the cold fluid now, and air is the hot fluid. Temperatures are the same. Hmm? Why did it say so? I'm not going to do a poll here. Do you think they are going to be the same or not? In the, you can write in the public chat window maybe. Okay, Burhan is also saying the same. So I think people are in consensus. So I see no reason not to show you directly what my interpretation of the problem is. Direct from my notes. Okay, so yeah, we can calculate heat capacity rate. We know the inlet temperatures. We don't need to know the outlet temperatures, right? That's a maximum heat transfer rate occurs when heat exchanger is sufficiently long, right? So it's infinitely long heat exchanger. And you calculate 140 by picking, which one are you picking? So you first reason that the heat capacity rate of air is less than the heat capacity rate of water. So we don't know what's going to happen to water at this point, but we are pretty sure that air is going to reach hot fluid inlet temperature. But now you know the cold fluid outlet temperature, cold fluid inlet temperature, you know the heat capacity rate, you can calculate heat transfer rate. That's what exactly what your friends did. They multiplied, they reasoned that let's pick the minimum of those two and multiply it with the initial inlet and inlet temperatures of hot and cold fluid, the difference between them. Then they said that, okay, the second scenario is different, but the result doesn't change. This time, the minimum heat capacity rate becomes that of the hot fluid, it's there. And then the temperature difference is the same, the result is the same again. That's the heart of what we are going to be method. We're describing it right now. And as long as I'm walking on the surface of Earth as an ME312 instructor, you can be rest assured that I'm going to be asking an exam question that will make you use this information that you practice today. So, all right, that's kind of a disclaimer for you guys. All right, let's discuss about the effectiveness NTU method. So that's actually, we have already covered the maximum possible heat transfer, right? Heat transfer that occurs when we have counterflow arrangement. Because we have figured that parallel flow arrangement is not going to allow this kind of behavior as the heat exchangers go, larger. And the heat transfer area is going to infinity, right? These two conditions are going to maximize heat transfer. So if the cold fluid heat capacity rate is greater than the hot fluid heat capacity rate, the cold fluid outlet temperature is going to approach that of the hot fluid inlet temperature. And therefore, you can calculate Qmax as the heat capacity rate of the cold fluid, hot fluid inlet temperature minus the cold fluid inlet temperature. Great. How about the other way around? This time the hot fluid outlet temperature is going to approach that of the cold fluid inlet temperature, and you can calculate this by saying that instead of that we are going to be calculating using the hot fluid heat capacity rate. But overall, if you consider if you're under these conditions, this is nothing but the minimum of maximum heat transfer is going to be given by minimum among hot and cold fluid, the minimum heat capacity rate multiplied by the inlet temperatures, right? I would like to write this a little bit more properly. That's an important equation. Leave some room there. Okay, that's the hot fluid inlet temperature minus the cold fluid inlet temperature. Let me describe what I mean by C min. That's the minimum of cold fluid and hot fluid. And similarly, if one of them is a minimum, the other one is simply going to be the maximum among two. Why am I saying that? Because I would like to define the ratio between them. The ratio of heat capacity rates is going to be the minimum versus the maximum. And it's always true that heat capacity rate is going to be between 0 and 1, or maybe it's going to be equal to 1 under a limiting case. Right, so this ratio will be less than 1 in general. And let's define effectiveness. That's indicated as epsilon. Therefore, we are going to see this definition as epsilon NTU method somewhere in your textbook. Epsilon is simply the ratio of the actual heat transfer rate divided by this ideal case. It's as a fin efficiency, right? And but then it is confusingly called effectiveness. So you can calculate this based on, again, the energy balance of cold fluid outlet temperature divided by cold fluid inlet temperature divided by C min, the hot fluid inlet temperature minus the hot fluid, also cold fluid inlet temperature. And you can also write this based on the other side of the energy balance as, what am I writing there? Net temperature, right? So this is actually nothing but it comes from the definition of the effectiveness NTU method, effectiveness and then energy balance. Then the heat transfer rate you can obtain as effectiveness times the maximum heat transfer rate possible. and that's going to effectiveness, C mean, CHI, I. Isn't that beautiful? Look at this equation. Let me call this equation 1. Unlike the log mean temperature difference, it doesn't really involve the outlet temperatures. If you know the effectiveness, based on the knowledge of inlet temperatures, you can calculate the heat flow rate. But then the problem is actually exchanged with determining this effectiveness. How to determine? Effectiveness is a blanket, quantity, right? It's actually describing what the relative properties of the fluids, like relative heat capacity rates, meaning the ratio of heat capacity rates, but also it is depending on how that heat transfer is realized. So we need to take into account two things. It's a function of what's called the number of transfer units, or NTU, and the heat capacity ratio. What is NTU? Let me describe. That's the number of transfer units I'm going to take a couple of minutes of you before we go, because I would like to finish this discussion, and it's not going to take long. And how we define number of transfer units? It has a formula. NTU is equal to UA divided by the heat capacity rate. It has no units because U multiplied by A is watt per Kelvin. The minimum heat capacity rate is also watt per Kelvin, right? And how would you interpret this? So imagine that's the length of the heat exchanger, and we are actually operating this heat exchanger between the bounds of the hot fluid inlet temperature and cold fluid inlet temperature. And in the extreme case, so let's imagine that C min is actually the cold fluid, corresponds to the cold fluid heat capacity rate. And in that case, you would actually obtain, again, imagine that this is a very long heat exchanger. It's actually approach to that of the hot fluid, right? So that's what we are getting. And for this very long heat exchanger, the area between those two curves, remember, it's going to be some measure of the maximum heat transfer rate. On the other side, if you multiply both sides with, let's say, this initial temperature difference, this is actually becoming some measure of some heat transfer rate. It's actually measuring the the effect of the fouling conditions, effects of the heat transfer configuration of the surfaces, the interface, but then also the heat transfer area multiplied by this limiting temperature. That's not the actual heat transfer rate, but it's a measure of how effective the temperature is being transferred across the interface. So it's actually measuring, imagine that's actually, that's something like Qmax, I'm sorry, Q star. And this is multiplied by UA, and UA is actually, this is the actual area. And in this case, the heat transfer is when the area goes to infinity, right? So that's the idea. Anyway, so that's kind of one interpretation of this. You don't need to think about like that, just stick with the formula. But understand that NTU involves the convection heat transfer conditions, involves fouling, involves fins because of this UA term. So we know that we can have this relationship and its reciprocal relationship. That means NTU can also be written as another function G of epsilon and CR. And in the next class, I'm going to show you some expressions for common heat exchangers. And you can take a look at section 11.4.2 for parallel law derivation, x derivation. And it's going to show you how you can actually go from log mean temperature difference to epsilon effectiveness NTU method. Okay, that's it. I took your time extra, I know, but I wanted to finish this slide. Thank you for your patience.